So yes, it is probably somewhat different to what we've heard this morning. So this is using synthetic aperture radar, but in a slightly different way, where we basically we interfere multiple images to try and actually estimate the displacement of the ground surface to infer whether it's from landslide movements, earthquakes, volcanoes. So I'll just give an overview really of some of the work we've been doing across New Zealand in terms of the monitoring we do, and also some of the sort of nice results we get. So how does it work? In essence, every time we're now getting these radar images acquired, since obviously Sentinel-1 was launched, this is roughly every 12 days. And what we do is we ignore the amplitude component. For most of what I do, I'm not really worried about that side of it. But what we do want is the phase component, and that basically gives a measure of the distance between the satellite and the ground. Now, if after subsequent acquisitions, the ground moves, we can essentially measure the phase shift in the phase component of the radar and measure the displacement of the ground, order of the millimeters accuracies. So if you look at the bottom left, so for a typical two images, phase 1, phase 2, if you look at obviously the raw phase is more or less meaningless. It's just a jumble of complex numbers. But when you perform the interferometry, which is in essence is just taking the difference between these two values, is if there's been a shift in the ground surface, you can generate these fairly beautiful maps of range change between the ground and the satellite. So in this particular case, this was from the Darfield earthquake in 2009. And if you were to try and interpret this, what you would say is for each of these contours or fringes, you just count these through. And in this particular case, each one is around 11 centimeters of movement, either towards or away from the satellite. And then we can build a picture, a complex picture of how the ground has moved. There's there's really a huge range of applications that we can use the technique for. So we've got things like earthquakes. So the top left, again, this is an example of the Kaikoura earthquake in 2016. With lots and lots of acquisitions, we can do things like urban monitoring for subsidence and uplift, or landslide within the urban environment. On the right also is just sort of more general landslides, with an example here showing some of these big sort of 2 kilometer scale coastal landslides along the Canterbury coast. We can do things like anthropogenic subsidence. So again, this is an example from Temporal, and this is the Wairaki geothermal, showing kind of 4 or 5 centimeters of subsidence a year. This is something I've never done, but you can, they have used it in the past to look at building monitoring. So in this case was the Eiffel Tower, looking at the sort of the swell of the iron girders between night and day. And then the bottom left is something we've been doing more recently, is using the very high resolution radar for doing monitoring on White Island. So if we come back to earthquakes, so we can use basically the technique to monitor the entire seismic cycle. So that's looking at the deformation caused by the earthquake itself, but also the period in between large earthquakes and also the period immediately after the earthquake. So in this example, again, this is Kaikoura. So this is 2 examples of interferometry using ALOS-2 data. So this is a fairly long wavelength signal that generally performs much better in New Zealand because of the vegetation issues. But what you can see on the left is an interferogram where each one in this case of these fringes is around 5 centimeters. And then on the right is another interferogram, but from when the satellite is looking in a different direction, which is why the pattern of displacement looks somewhat different. But what we can do is then we can take all this information and we can generate models to estimate how much the ground slipped and which faults were kind of the main players in these earthquakes. And what for Kaikoura was really, really useful is that it was really the INSAR data that first kind of pointed towards this very, very complex rupture, and that most of it occurred within sort of the upper plate of New Zealand, whereas global seismologists were all arguing and saying that it was a result of this kind of a subduction event like we've seen in Tokyo or in Japan in 2011. But actually the interferometry kind of proved them wrong. Other things we've started to move into now is to look at what we call the interseismic. So this is looking at the period between earthquakes to try and get an estimate of kind of the long-term motion of New Zealand. So this on the left is just showing essentially this is the line of sight component of the deformation field projected into the satellite. And on the right-hand side, we have to do some kind of some tweaking using the GPS. On the right is showing then the estimate we get of the vertical component of the deformation field, and then each of the bigger dots are a comparison with the GPS data. What I've not mentioned and what's important is the INSAR is, unlike GPS, which is an absolute measure, the INSAR is only a relative measure because you never really know where zero is within your, say, your sort of larger interferogram. And so when we try and calibrate, what we're really trying to do, we try and tie the INSAR into the GNSS or the GPS reference frame. And that's what's shown in these two profiles. And you can see, so the blue data with the error bars is the INSAR deformation, and then the red triangles are what you get from the GNSS over the same period. And what we see is for the east coast of New Zealand, is we can see this overall subsidence pattern up to rates of around 8 millimeters a year. And this is essentially caused by this ongoing process of subduction, where in our case, we've got the Pacific plate diving beneath the North Island, which essentially is just pulling down that east coast. I say we want to calibrate this using this historical data from ENVISAT. Because of the quality of the data is not always easy. And this is kind of two examples, one where it works and one where it doesn't work quite so well. So on the left is looking around Napier, and you can see again the different colored dots. The big ones are the GPS and the others are from INSAR. And we get a fairly good agreement across the region. If we come to the Southern Alps, for example, we have some other issues. Because of the terrain, we do tend to lose some signal in the radar measurement. And also what we see is within some of these glacial valleys, we're seeing this kind of fairly broad scale, or valley-wide subsidence on the order of 5 millimeters a year, which we think is probably to do with the compaction of the old river channel. But if you look at the GPS, then the whole region really should be uplifting. So what we've got this problem of sort of competing processes, which we need. When we're trying to look at this, we're trying to look at the bulk tectonic motion of New Zealand. We need to try and separate some of these features out, which isn't always trivial. What we can do is, when we've got these kind of national data sets, what we've started to do then is to take the coastal estimate of say the vertical, and that's been fed into sort of the latest generation of sea level rise projections, where you can actually include the uplift or the subsidence along the coast. Obviously, what you find is in areas which are subsiding, sea level becomes more problematic. Other areas where you may have uplift, then it kind of somewhat compensates for that ongoing sea level rise. We also we can take the same kind of data sets and we can feed into the latest seismic hazard models. And what we can do is then to try and use these deformation data to try and pinpoint which faults through New Zealand have got higher probabilities of rupture in the future. And so this is just an example looking at faults which have got more slip deficits. So that means they've got room to move in the next sort of 50 to 100 years. Moving to the side slightly, so we're also then using it quite extensively for volcanoes. The main focus product I've worked on most recently is for Kari, White Island. And we've got quite a good time series now from 2015 using a fairly high resolution 1 meter Terasar X data. And on the bottom then is, again, these two look directions from the satellite showing you the deformation. And what we really can see in this case is that this sort of on the back wall of the island, we're seeing these very, very strong essentially landslide signals where that back slope is slowly kind of collapsing in towards the vent. At the same time, we can, unlike other sort of ground-based methods that are obviously more or less now impossible on White Island, is we're able to pick up deformation really, really close to sort of the main vent areas. and in kind of areas now which are sort of not possible to go to on foot because of obviously the hazard involved with having to go and stand on a vent. And on the right is just looking then at these time series histories, and then these two black lines are just the two timings of the eruption in 2016 and then the one in 2019, where you really see this back slope take off following that eruption. This is another example. So this is one of these 25 centimeter radar images over White Island that we've been able to acquire again from Terrasar. And what this is really now allowing us to look at really fine details in the deformation. And so this particular interferogram, these little fringes just around here showing little lobes of uplift associated with a gas pulse coming through the vent system at the back of the island. But at this scale, we can pick up things that for some of the course of the kind of Sentinel missions are just never going to be able to capture. I said that I generally don't look at the amplitude, but actually for White Island, the amplitude imagery becomes very useful. So the right-hand side is an image just before the 2019 eruption. And on the left is the typical webcam view that we used to acquire from the webcam, which was situated just up here on the top of the slope. And because of all the steam and basically often the view is obscured. But through the radar, what we can do then is look at the sort of temporal time series of and the evolution of the back of the island using the radar instead of optical, which obviously can be hampered by clouds, or in this case, steam. And I'll try this video, but it's unlikely to work. But what you can see, this is just a temporal kind of evolution of looking really at the lake fill and emptying. And also we can start to pick up ash deposits that are coming out of the vent area. The challenge with this obviously is it's very hard actually to calibrate the amplitude imagery into a sort of a meaningful signal. And that's something that is kind of work that is ongoing. And then the final couple of slides. Where we're trying to go in the next couple of years is really to generate a national deformation data set that will hopefully cover the bulk of New Zealand. Because of the sort of regular acquisitions we get from the Sentinel mission, we're starting to be able to do kind of these very sort of 6 to 12 day time series on a sort of nationwide scale. So this is an example for Auckland over the State Highway 16 bridge development, which you can see since they finished the construction work in 2016 has essentially started to subside, probably due to the sort of compaction of the underlying sediment underneath the new highway. What's challenging is that the processing is very computationally expensive. The data sets are very large and it's very time consuming. So what we've done is basically to try and do it. We've done a joint collaboration with a group in the UK who are essentially going to provide the high resolution data set for us so that we can build these kind of very high spatial resolution data sets. So again, here are just two examples. This is obviously over the centre of Auckland. And you can see there's a lot of, some of these little signals are all to do with little minor landslips, sometimes where there's been construction and you see the substance following. To looking at longer term substance, so this again, this is a town, I forget the name of the town, to the south of Auckland, where we see this kind of spatially varying substance across the town. Now, at first glance, there's no real reason why the town should be subsiding. But then when you start to combine other sort of historical data sets and historical optical data sets, what you find is that most of this town around 5 years ago didn't exist. And it's gradually been built up over that time. And what we're seeing here again is this substance is from essentially the compaction of the ground fill that was used for building the new housing and sort of in this case, and also some factories. So the real challenge going forward is when we start getting all this deformation data, like many people have talked about the volumes of data, we're going to have to start really concentrating in on how we accurately mine the data sets to get meaningful data out and get meaningful displacements that don't that actually represent what's going on both on the ground, but not just kind of obviously potentially could spook people if they look at their house and see that their house is subsiding. So there's a very rapid run through of some of the work we've been looking at. but hopefully you can see again, InSAR itself it's becoming a very powerful tool for monitoring deformation of the Earth, both at different spatial and temporal scales. Potentially you can get imagery now within hours of there being an earthquake or a volcanic eruption. And so it can really guide kind of boots on the ground in sort of the early response mode. Obviously, more and more satellites are continuously being launched, so we're able to get better, smaller rates, bigger areas. And hopefully, yeah, with sort of some of these future missions and the developments that are ongoing in sort of the processing of these data, it could become a much more standard technique for kind of, yeah, for more people to access. And that was me. Thanks very much.